Hi, I'm Bob. Welcome back to 5 Minute Econometrics, a program focusing on introducing fundamental econometric concepts and estimation methods. Today, we will examine the consequences of adding an explanatory variable to the model. We will explore how it affects the standard errors of the OLS estimates. Suppose we have the following regression model. Now we add a new explanatory variable xj plus 1 to the model. What will happen to the standard errors of xj's coefficient estimate beta j hat? The standard error of beta j hat is the square root of the estimated variance of beta j hat. The estimated variance of beta j hat equals the estimate of error variance, sigma square hat, divided by the total sum of squares of xj, SSTJ, times 1 minus rj squared. There are three components in the formula. The estimate of error variance, sigma square hat, can be computed from the residual sum of squares, SSR. The total sum of squares of xj, SSTJ, describes the variation of xj. Rj squared is the r squared from regressing xj on all the other explanatory variables in the model. It describes how much of the variation in xj is explained by all the other explanatory variables, or how strongly xj is correlated with other explanatory variables. With the formula in hand, we can now analyze how adding one more explanatory variable affects the standard error of beta j hat. It is equivalent to finding how it changes the estimated variance of beta j hat. Adding a new variable makes the changes in two opposite directions. On the one hand, the residual sum of squares, SSR, will reduce because the new explanatory variable helps to explain part of the variation in the outcome variable y, leaving less variation for the error term. In large samples, the degrees of freedom converge to n. The estimate of the error variance, sigma square hat, decreases in large samples. It will lead to a smaller estimated variance of beta j hat and a smaller standard error of the estimate. However, on the other hand, adding a new explanatory variable could exacerbate the multicollinearity problem, which means the new variable could be highly correlated with xj, leading to an increase in the rj squared. Generally speaking, we don't know which effect dominates. Notice that the total sum of squares of xj, SSTJ is unchanged. There is a special case in which the new variable is not correlated with xj. In this case, the rj squared will not be affected by the new variable. In other words, the new variable does not introduce multicollinearity. As long as the new variable has some explanatory power, the estimate of the error variance, sigma square hat, will drop, and therefore the standard error of beta j hat will fall. A smaller standard error means a more precise OLS estimate, since its confidence interval becomes narrower. The t-statistic becomes larger, and the OLS estimate becomes more statistically significant. For example, in the parents' income and children's hourly wages example we have used in the past topics, we regress workers' hourly wages on their parents' average income during their childhood to find the intergenerational earnings, mobility, and persistence. Suppose the sample is from random surveys. The variable of interest, parents' income, should be uncorrelated with workers' demographic characteristics. It is possible to get a more precise OLS estimate by adding workers' gender, age, marital status, region of residence, and race to the model. If these factors affect workers' wages and are uncorrelated with parents' income, then the standard error of the intergenerational earnings mobility coefficient will decrease, at least in large samples. Today, we have discussed the change in the standard errors of adding new explanatory variables in the model. It will either increase the standard error or decrease it, depending on how it affects the error variance and whether it introduces multicollinearity. In the special case where the new explanatory variable is uncorrelated with the existing explanatory variables, adding more control variables will produce more precise OLS estimates. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.